Hello, hello. Today we are going to go over Chapter 5, Lecture 13. We're going to be looking at learning objectives 7 and 8. So we're going to be looking at enthalpy and amount. Enthalpy is a extrinsic property, so it's going to be based on the amount of substance you have. And then we're going to be looking at our calorimetry, so um, what happens when you contain a system as close as possible um, and look at that heat flow directly. Okay, so first let's start with some enthalpy fun facts. So enthalpy is a state function. Remember that our enthalpy itself, delta H, is equal to delta E plus P delta V. All these components here are also state functions. And since all of these are state functions, this will therefore be a state function. Okay, as I said just a minute ago, it's a extrinsic property. So our delta H is given in generally kilojoules per mole. Our delta H of a reaction is going to have the same magnitude um, of value, uh, whether it's a forward or reverse reaction. We're just going to flip the sign if we have a forward or reverse or reverse. So delta H of reaction will have the same magnitude for both the forward and reverse reactions. The sign will just be different. So if we have delta H in the forward direction, that'd be the negative delta H of the reverse direction. And when we look at our delta H of our reaction, it will always depend on the state of the products and reactants. So the value of delta H depends on the states of the reactants and products, as in our physical states. So if you have a delta H value for a particular reaction, it'll generally show what states the reactants and products are in, and they have to be in those states for that delta H to be valid for that reaction. Okay, so let's try an example of delta H as an extrinsic property. So let's say we've got the combustion of methane in its gaseous state. Um, this combustion of methane is negative 890 kilojoules per mole of methane. And so this is a known. Combustion of methane in the gaseous state is negative 890 kilojoules per mole. And we'd write this as CH4 gas plus O2 gas goes to CO2 gas plus H2O gas. And our delta H of our reaction is equal to negative 890 kilojoules per reaction or per mole. And then, of course, we would need to balance that like so. So this is 890 kilojoules per 1 mole of methane, or per 2 moles of oxygen that are reacted, or per 1 mole of carbon dioxide that is produced, or per 2 moles of water produced. So the question is, how much energy is released when 25.8 grams of methane is combusted? And whenever we see released, we know this is going to be a negative sign, right? Okay, when we're approaching a problem like this, we know that we have a delta H of reaction equal to negative 890 kilojoules per reaction, or kilojoules per mole of methane, right? So we have moles of methane, grams of methane. We need to convert this grams of methane into moles of methane, and then using this, we can go into energy. So we'll take our 25.8 grams of methane. We'll take our molar mass of methane, which is equal to 16.043 grams, and convert that into moles of methane. And then using our enthalpy as a conversion factor, we can go and figure out our joules of energy that are released, so a negative value. And then we generally want this to be in kilojoules, and this is 2 sig figs. So our answer will be in 2 sig figs. Oops, I put that in kilojoules. Joules. Convert that into kilojoules. Oh, no, I was right the first time. Just put that in the correct number of sig figs, giving us negative 1400 kilojoules of energy released. And it's as simple as that. Okay, a lot of times we're going to look at enthalpy when we look at calorimetry. So calorimetry, that's going to be our measure of heat flow. Remember that um, heat is going to flow from a hotter object to a cooler object. So we're going to be looking at that heat flow from the hotter object to the cooler object. Within calorimetry, we have something called a calorimeter. That is the device used to measure heat flow. Okay, so when we're looking at calorimetry, a lot of times we'll be looking at what's called constant pressure calorimetry. So most calorimetry that we look at is constant pressure calorimetry. If we remember, in that case, if we have constant pressure if we're looking at that heat flow, then it will be equal to our enthalpy. So generally, calorimetry is going to measure delta H for a reaction. Okay, so the most common type of calorimeter we look at is called a coffee cup calorimeter. For us, it is not very helpful in real life, but in here we look at a coffee cup calorimeter, and what a coffee cup calorimeter has is two coffee cups embedded in each other for extra insulation, and then generally there's some type of lid that holds it all in place. And within that lid there's going to be a thermometer. So we're going to have a top to our lid, or a top to our calorimeter rather, and then, as I said, we've got two cups embedded within each other for extra insulation. And then within the second coffee cup, we usually have water. So this is going to usually be a water solution. Water is our solvent. And we usually do reactions in here. So reactions are done in the water. So almost always we're looking at the change in temperature of the water. So the water is not involved in the reactions, but they're going to be the surroundings, right? So our water is our surroundings. So they're going to exchange heat with our system. So we'll be indirectly looking at our system by looking at our water in calorimetry. So what are we actually looking for when we're doing calorimetry? Generally, we're looking at specific heats of things and heat capacities. So if we add heat to a substance, it's going to get hotter. So when heat is added to a substance, that substance gets hotter. And it heats up. However, the amount of heat that's required to heat up that substance is going to vary based on the material. So anything will heat up if heat is added. So more heat. But of course, we're going to have substances requiring greater amounts of heat to change temperature versus other things. So substances require different amounts of heat to raise the temperature of the substance. We can think about it this way. If we think about something that is metal versus water, if you're heating up a pot of water, the metal, the pot itself will get hotter quicker. For water, the water takes a lot longer to heat up than that metal does. And that's because it requires more heat to raise the temperature of water versus a metal. So we would say that a substance that requires a greater amount of energy to heat up or to increase its temperature has a greater heat capacity. And our heat capacity is basically the amount of heat required to raise a substance temperature by 1 Kelvin or 1 degree Celsius. And these are going to be interchangeable in this particular case because it's a change in temperature where the change in Kelvin will be equal to the change in Celsius. So we look at two types of heat capacities. So for a pure substance, we can either have a molar heat capacity, which is given as uppercase C subscript M, or which is given as a uppercase C lowercase s, and our molar heat capacity is going to be the amount of heat that's required to raise 1 mole of a substance by 1 degree Celsius, while our specific heat is going to be the amount of energy that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So our joule or our molar heat capacity is in joules per mole times by Kelvin, or joule per mole times by degrees Celsius. These are equivalent to each other. Our specific heat is joules per grams times by Kelvin, or joules per grams times by degrees Celsius. So our specific heat or our molar heat capacity, we can write it kind of as an equation. So our molar heat capacity is going to be equal to the quantity of heat transferred and this is going to be in joules, divided by the moles of the substance, and this is going to be times by the temperature change observed. And this can be in degrees Celsius or Kelvin. Does not matter, either one. Our specific heat Very similar equation, but now we have grams instead, so we'll have the same top quantity of heat transferred in joules. But now we're going to divide this by the mass of the substance in grams times by our temperature change in either degrees Celsius or Kelvin. Now, we have a lot of they have tables of specific heats, and you guys are not required to memorize specific heats, but some specific heats that you might want to know, or some specific heats you might want to look at. Water in the liquid phase has a specific heat of 4.184 joules per grams times by degrees Celsius. So that's one of our substances. Liquid water has a specific heat. Gaseous water and solid water, so water vapor and ice, are going to have different specific heats because they require different amounts of energy to change that temperature. And then we have things like metals. Aluminum in the solid phase has a specific heat of 0.90 joules per grams times by degrees Celsius. So this is going to be a much lower value because it is a lot easier to heat up metal. Mercury in a liquid phase, 0 per grams times by degrees Celsius. And of course, each one of these can also be times by Kelvin. So let's try a specific heat problem. So if we have 25 grams of copper, we want to know what the specific heat of copper is if it takes 487.5 joules of heat to heat 25 grams of copper from 25 degrees Celsius to 75 degrees Celsius. So we have 25 grams of copper. If it takes 487.5 joules to heat the copper from 25.0 degrees Celsius to 75.0 degrees Celsius, what is the specific heat of copper? What is its molar heat capacity? Okay, so let's look at both of those. So if we have our mass of copper, we have our energy of energy to heat, our heat energy, and we have our delta T. We can put all of these into our specific equation where Q is equal to mass times by specific heat times by delta T. So this is our heat, our mass of substance, whatever we are observing, our specific heat, and our change in temperature. Again, it does not matter if it's Kelvin or degrees Celsius, but once you've started, keep that as your specific heat. Or sorry, as your temperature change. So we have 487.5 joules. It's going to be equal to our 25.0 grams times by our specific heat times by our delta T, 75.0 degrees Celsius, minus 25.0 degrees Celsius. Multiply all this out. We get our specific heat is equal to 487.5 joules divided by 25.0 grams times by 50.0 degrees Celsius. And we get a value of 0.39 joules over grams times by degrees Celsius. Now, if we want to go from a specific heat to a molar heat capacity, we need to look at our molar mass of copper. So right now, we have 0.39 joules per 1 gram of copper times by degrees Celsius. We can then say there are 3.546 grams per 1 mole of copper. And when we multiply that out, we get 24.8 joules per mole times by degrees Celsius. Oh, there's supposed to be 8 here. 8, 9. 8, 9. So now we have our molar heat capacity and our specific heat. Good times. Moving on, let's look a little bit more at calorimetry. One other thing within calorimetry is constant pressure, not constant pressure. We have our constant volume calorimetry. So what we've looked at so far is constant pressure calorimetry. So let's just real quick summarize that. So we have a coffee cup calorimeter, and here we're doing a reaction in water. And remember, it is our surroundings. So we monitor our surroundings. To get information about our system. So our heat of our system, so whatever heat is absorbed or released by the system, is going to have an opposite sign as the surroundings. So if a system releases heat, it'll be absorbed by the surroundings. If a system needs to absorb heat, it's going to be taken from our surroundings, so our surroundings will lose heat. So these are going to have opposite signs. So almost always you're going to be looking at the Q of your surroundings, which is in this case the Q of our water or our solution. So when you're solving for these, the first step is going to be our Q of our solution is equal to the mass of our water times by the specific heat of our water times by the delta T of our water. And then we'll take that Q of solution, remember our surroundings, to be equal to the negative of our system, whatever our system has to be. And then we will have this piece of information. So then we can put this into Q of system is equal to the mass of our system times by the specific heat of our system times by the change in temperature of our system. So it's a reaction or a metal or something like that. Our other type of calorimetry that we look at is a constant volume calorimetry. Okay, so this is going to be bomb calorimetry. So it's a self-contained reaction, but pressures are going to be built up here because it's completely enclosed. So generally, we're looking at combustion reactions. And they are carried out in a sealed bomb. And this is because it could withstand the extreme pressures. Okay, so this is, we're not here looking um, at our enthalpy here. We're actually going to be looking at our internal energy instead. So in bomb calorimetry, we are looking at internal energy, not enthalpy. Okay, I would say just like up here when we said, where is that? Ah, if we have a constant pressure system, then our heat will be equal to our enthalpy. In the case of constant volume, if we have our heat at a constant volume, that is going to be equal to our change in internal energy. And that's because there is no work. Because there is no volume change. Right, so here, our delta E is equal to Q plus W. If this is a constant volume system, there's no work. So our delta E is just QB. Now, the reason that they do this is these are going to be very accurate measurements for determining the energy of reaction. But it's going to be, again, pretty similar to what we see with our constant pressure calorimetry. We're going to be looking at the change of temperature of water in order to see how much heat is released from a system. Now, um, with this, we aren't usually looking at a amount. Instead, we use steps or the procedure. Let's go with procedure. So a standard is used to determine the calorimeter constant first. So the very first thing that's done in constant volume calorimetry or our bomb calorimetry is we need to figure out our calorimeter constant. And it's very easy. You have a known Q of a reaction, and you'll set that equal to the calorimeter constant or negative calorimeter constant times by the change in temperature. So you're going to look at that change in temperature of your water for a known substance, and you'll solve for your calorimeter constant. Once you have that calorimeter constant, you can use that to solve for the amount of heat of an unknown. So then the calorimeter constant is used to determine the Q of the reaction for an unknown. So very simple. Let's try. So let's say that we have 1.000 grams sample of octane. So it was burned or combusted in a bomb calorimeter. Okay, and in the bomb calorimeter, there was 1,200 grams of water. At 25 degrees Celsius. Okay. After the reaction, the water temperature increased to 33.20 degrees Celsius. If the calorimeter constant is 837 joules per degree Celsius, and the specific heat of water is 4.184 joules per grams times degree Celsius. What is the heat of combustion of octane in kilojoules per mole? So, the very first thing we want to do is we want to figure out so we have water. Anytime we have water, we want to use that water and determine how much energy is absorbed or released by the water. So, water itself, 4.184 joules per grams degree Celsius. We have a temperature change of that water, and we have a mass of that water. So this is just a normal specific heat problem where we take the Q of our water, set it equal to our mass of our water, times by the specific heat of our water, times by our change in temperature of water. So Q of our water is equal to our mass of our water, 1,200 grams, times by specific heat of water, times by our change in temperature of water, 33.20 degrees Celsius minus 25.00 degrees Celsius. And when we multiply all that out, we get a Q of our water equal to 41.2 kilojoules of energy. So now we know how much water or how much energy was absorbed by the water that must have been released from our calorimeter. Right? So we can then look at the heat absorbed by the calorimeter. So we have the heat absorbed by our water right here. Now we want the heat absorbed by the calorimeter. So we're going to take our Q of our calorimeter. It's going to be equal to our calorimeter constant times by our change in temperature. And this is going to actually be of our water. So we put these values in. Our calorimeter constant will be given generally. And then our change in temperature of water is at 33.20 degrees Celsius minus 25.00 degrees Celsius. When we multiply all this out, we get 6.86 kilojoules of energy. To determine our total amount of energy, we take the heat absorbed by the calorimeter, the heat absorbed by the water, and combine them. So total heat is going to be 41.2 kilojoules plus 6.86 kilojoules, giving us 48.1 kilojoules. So this is total heat absorbed. And this heat absorbed was released by the burning of our octane. So our Q of our reaction will be equal to negative 48.1 kilojoules. A change in the sign because we're going from an absorption of heat to a release of heat. And then now that we have this kilojoule amount, this kilojoule amount is based on 1 gram of sample. Right, so we'll divide this by 1.000 grams of octane. And now we can go from grams of octane into moles of octane by taking our molar mass of octane, which is 114 grams per 1 mole of octane. And when we multiply that out, we get negative 5,483 kilojoules per mole. Very, very large amount. Okay, that is everything. Thank you guys so much. I'll see you next video.